OpenAI's GPT-4 is believed to be a mixture of experts, but now there is an open source mixture of experts called Mixtral available. I'll be showing you how to inference the model, how to fine tune it, and also telling you a little bit about how mixture of experts work. Let's take a look at what we have for agenda. I want to explain why to use mixture of experts over a normal model. Then I'll give some detail around how mixture of experts work. I'll start off with basic transformer design and show you what a single layer looks like in a standard transformer, because that will make it easier to understand how a layer is different in the mixture of experts design. Then I'll show you how to inference using a one-click template for RunPod and give you some tips on the best ways to inference right now. I'll then walk through a fine-tuning example. It'll be an example for function calling, but a lot of the tips I give will be applicable to unsupervised or supervised fine-tuning scripts that I've gone through in the past as well. Then last off, I'll leave you with some tips on future work that I think will be done to incorporate mixture of expert type designs into common packages and tools you might be familiar with. The idea with a mixture of experts is that instead of asking a single model for an answer, you have a little module called a router that will decide which expert to ask. For example, there might be 8 different experts to ask, and instead of asking one very large expert, the router will pick one of these smaller experts to give you an answer. In short, what it allows you to do is to get the quality of a very large model, like a 70 billion model, but doing it only with the speed of a small model, perhaps like a 13 billion model. The reason is that asking any one of the smaller experts, once you've chosen which one is best suited to the question, it's able to calculate the answers and give you the next tokens much faster than if you asked a very large model. However, because you have all of these experts, they're able to cover a span of knowledge that is somewhat equivalent to what a very large model would be able to cover. Let's take a deeper look into how mixture of experts are designed by starting with the basic transformer. So if you're working with Llama 2 or many of the models out there, the basic Mixtral model, Falcon, the Yi model, DeepSeek, any of these, or indeed GPT 3.5 most likely, you're looking at a multi-layer transformer that will take in inputs like how are you, and it will help to generate the next token, which in this case is shown as predicted as today. These models consist of a series of matrices that will convert first the words into numbers and then propagate these numbers through a series of layers to calculate the next token prediction. Now you can see here I've shown, I think, 7 different layers. Often these models have anywhere between maybe 20 and 50 or 60 different layers. And these layers all are structured in a similar way. So their architecture is the same in each layer, but the exact values of the matrices used for the multiplications will be different in every single layer. Now, there are 2 ways that you can increase a transformer in size. One is you can have more of these repeating units or layers, and the other is you can make each layer bigger. So you can make the number of matrix parameters within a layer larger and larger. Let's take a quick look here at what happens inside a layer. There are 2 things that happen within a transformer layer. The first is a feed-forward mechanism. What a feed-forward mechanism does is take the inputs, for example, how are you, and multiply each one by some kind of a constant. So you could have A times how plus B times R plus C times U. Now you'll say, how do you multiply words? Well, remember, the words before they go into the first layer are converted into numbers. So how might be 0, 0, 1, R, and U. So when I say A times how, I mean multiplying A by a number representing the word how. So this is a feed-forward layer. It's a constant times an input plus a constant times an input. And you can expand the size of this linear layer or feed-forward layer just by adding more constants. So here you can have a node or an output, you can think of it as, which is A times how, B times R, and C times U. You can easily add another node to that layer to make it bigger and have D times how plus E times R and F times U. F times U is coincidental. Now, the choice here of these parameters is determined by the training process. So all of A, B, C D, E, and F are all going to be optimized during the training process. So to recap, if you want to increase the complexity of a feed-forward layer, you can keep adding more nodes. And what you do is you're going to connect the output of the previous layer to the input of the next layer. So here we're receiving information from the previous layer and passing on to the next layer. Now, of course, on the very bottom layer, we will very distinctly see that the words "how are you" are being passed up. As you move towards next and next layers, the meaning of the output becomes more and more abstract, so it wouldn't be possible to attribute, say, the output here to any one particular word. The important thing about a feed-forward layer, though, is that it's linear. It's just these constants multiplied by effectively the inputs in order to generate outputs. Now, the second thing that happens in a transformer layer is called attention, and this is the key feature of the 2017 paper "Attention is All You Need" that makes transformers very effective. And what this attention mechanism does is it allows a given word to be compared to other words. So for example, if we have "how are you," with attention, the word "you" is compared, which mathematically we can describe as a multiplication. The word "you" is compared with "how" and is compared with "are." And this allows the transformer to look back at the past and look at interactions between words within the sentence. And that's really important for getting good accuracy in predicting the next word. And just like I showed, these words are represented by numbers. You can have those numbers multiplied by constants. So here I've got G, H, and I. And again, these are trainable parameters that will be trained when we backpropagate through the model during the training process. So here's a very simple attention mechanism, just with one node. But you can easily, if you want to add more complexity to the model, you can add multiple nodes within that layer. So you could have constants G, H, I, J, K, L, and keep going and going if you want to make your model larger and larger. Now here's all of this put together in the original transformer paper, and you can see they're doing both things I mentioned, the attention right here and the feed forward, and they've got them in series. Now, in fact, you can put them in parallel, and some of the more recent papers are looking at that mechanism. But the important thing is that each layer, when we talk about a transformer like GPT, it typically has two mechanisms. It has the feed forward and it has the attention. So this is how the original transformer works. And as I mentioned, if you want to make a transformer more complex, you have a few options. You can increase the number of layers, so increase the number of repeating units of this. Or you can increase the size of the feed-forward layers, so you increase the number of trainable parameters in your feed-forward, and or you can increase the size of the attention mechanism within the layers, so GHI or whatever constants you're using to represent the matrices of the attention. Of course, when you make your model larger and larger, it's able to better fit the data that you're going to use to train it, but it's also going to make the model slower, because you've more calculations, you've more parameters that need to be multiplied in order to get from input all the way through your output. And this is how you get to the idea of the mixture of experts. Basically, you keep on increasing the size within each layer, you keep on increasing the number of layers, your model gets better and better, but as you try and make it a better fit to the data by adding parameters, it becomes slower. So what mixture of expert does is it actually keeps the same attention mechanism within each layer. So here we're looking at one layer, which is going to be replicated, say 30 times throughout the transformer. Typically in mixture of experts, we keep the attention as is, so we don't change that. But what we do in the feed forward layer is instead of just having one single set of nodes or one single layer architecture right here, feed forward, we split that into multiple matrices. And so rather than just having one, you can think of it as one big matrix for the feed forward, we split that into maybe 8 matrices. And rather than every time running through that full big matrix, we have a gating mechanism. And the gating mechanism decides which one or maybe 2 of the smaller matrices we're going to use every time we pass forward. So if we've a token that come in that says how, it'll go through attention, it will get to the gate, and the gate will decide, okay, this is the token how, we're going to send it to experts 1 and 2 out of the 8 experts. And that means we now only need to run the computations through 2 out of those 8 smaller experts rather than running through one very large matrix. So what the mixture of experts does is it means we cut down, if we're choosing only 2 out of 8 experts, we're cutting down the computation that we need by roughly a factor of 4. Just to make it concrete, let's head over to the model card for Mixtral 8x7b Instruct. So here we have a mixture of 8 experts, each of which has 7 billion parameters. And we can go in here to the files and take a look at the size of the model when it's saved in 16-bit format. So here there are 19 of these safe tensor files, and they're each about 5 gigabytes each. So if you multiply that out, you get about 45 gigabytes for the model size in total. If you were just replicating 8 of the 7B models, 8 sevens is 56, so it should be 56 gigabytes instead of 45. However, you'll remember that the attention mechanism is the same in each expert. So every expert uses the same attention mechanism for the same given layer. So layer 29 of each expert, the attention mechanism is going to have the same variables A, B, C, or the same constants A, B, C as the rest of them. And that's why it's 45 instead of 56. Now, if you think about larger models, a model that has roughly about, say, 45 billion parameters, that's, somewhere around 2/3 the size of a Llama 70B model. However, because only 2 of the experts, so that's 2 out of 7, are being activated at any one time, it's basically giving you the speed of a 13B model, which is like 2 times 7, very roughly. But it's giving you the size of knowledge of a model that's about 45 billion parameters in size. So that's a theoretical overview of Mixtral. It's very roughly a 50 billion parameter model, but has an inference speed of a model that's only 13 billion parameters in size because it runs 2 experts roughly around 6 to 7 billion parameters each. Now, additionally, Mixtral makes use of 7B Mistral models that are trained on high quality data sets. And these data sets have improved since the ones that were used on Llama 2, for example. So when I say that it's like a 50 billion model, that's just talking about the number of parameters. Probably in terms of performance, it's performing like an even larger model because those larger models are older and the data sets were not of as high quality, I assume, which leads them to have lower performance than the Mistral model. Okay, with that, let's dive into an example of inference, how to run this model, and then I'll talk a bit about fine-tuning. The easiest way to run inference is to start off with a one-click template. This is if you want to set up an API where you'll be able to make calls, including parallel calls, and get responses from Mixtral. Now, those of you who've already purchased the Advanced Inference repo, you'll be able to find a link right here under RunPod. You'll see under TGI that there's a one-click template here. And those of you who haven't purchased it, you'll be able to see the link just below in the description. So I've clicked on that link, and this should pop up the Mixtral Instruct API by Trellis. And I'm now going to pick a GPU. Now, just a few notes on picking the GPU. In order to load the model fully into your VRAM, you're going to need to have roughly 100 gigabytes, which is a lot. That's even more than an A100. So it's very difficult to run the model in 16-bit precision just on one GPU. I don't think it's possible. However, if you run it in 8-bit quantization, EETQ with TGI, you'll be able to fit it in 48 gigabytes. If you run it in bits and bytes NF4, which I'll also show you briefly, you can even run it probably in 24 to 26 gigabytes of VRAM, and maybe you can squeeze it onto a slightly smaller GPU. So the GPUs I'd recommend, and I'm going to use an A6000 here, has 48 gigabytes of VRAM, so it will fit it in 8-bit precision, which is under 48 gigabytes. You could also run for improved speed on an A100, which is more expensive, but should give you a little better performance in terms of speed. So we'll click on deploy, and we can check out the custom parameters. You see here that it's already set up by default as EETQ, which is 8-bit quantization. And you can see here how I've chosen. Let me increase my screen size. You can see how I've chosen the model, 8x7b Instruct, and I'm running the latest version of the Docker image for text generation inference. So I'll set those overrides and then I'll click continue and deploy to get this running. Here I am with my instance up and running, and you can see that about 69% of the disk space have been taken up because there's just over 100 gigabytes of the weights that have been downloaded. And we can check in on the logs here. And what we can see is that all of the weights have been downloaded. This can take some time. And I noticed there can be some bugs downloading the weights. So if that is the case, what you can do if it gets stuck after downloading a few shards, you can just click here and click on Restart Pod. That means you won't lose your progress on any installation or on the weights that have previously been downloaded, and the pod will just pick up and continue to download more of the shards. So you might have to do that once or twice to make sure all 19 shards have been downloaded, and then the model should start to be loaded onto the GPU. And I've just opened up the logs on the pod, and you can see that after quite some time, all of the shards have now loaded and we're ready to query the API. Now for that, we do need the run pod ID. So we have the pod ID here that I'm going to copy, and I'm going to paste it into the environment variables on my repo. So I have my advanced inference repo open up here. And in the environment variables, right here, .env, I've just enabled the API endpoint for runpod. And in here, I've pasted in the pod ID so that we're ready to query. I've also put in here the model name that we're going to query. So we're all ready now to make calls to the API. And we're going to do that with TGI-speed. You can check out the inference video I made, but this is going to send a quick question and ask for a long essay on the topic of Spring. So let's just do that. TGI Python tgi-speed.py, and we'll see how fast we get back a response. And then what I'm going to do is a concurrent test rather. So here we have TGI speed concurrent, and we're going to try and ping with 20 requests within with spacing of 1/8 of a second, and we'll see how the server is able to handle that load. So I'll just save those updates, and still waiting on that first query to come back. Here we go. So you can see an example of this response. I've asked for a maximum of 500 of tokens, and we can see that the time for generating that was just under 30 seconds, and the tokens per second is about 19. So with EETQ using an A100, you're going to get about 19 tokens per second. And now let's try and run a concurrent test, TGI speed concurrent.py, which is the same request, but again, we're pinging it every 1/8 of a second, and we're doing it 20 times. So all of those requests will end up overlapping, and the language model will have to handle them all in parallel. So we want to see if that's going to slow things down. Okay, we've just gotten the results back, so you can see all of the requests going through, and the requests have also taken about 30 seconds each for a total completion. Of course, you would see the tokens come much before that if they're being streamed. And the tokens per second here is about 17. The lowest I see is 1694, 1681. So there's a very small penalty here for doing parallel requests, which shows you that with the EETQ form of quantization, that 8-bit, you're able to handle a lot of parallel requests going to the server, and it's able to deal with them without penalizing the time per token much at all. Now, let me briefly show you how you can use another form of quantization. So if you go in here to the pod and you click on Edit Pod, you'll see where we have previously set Quantize EETQ. Now, instead of Quantize EETQ, you can reset this to bits and bytes and -NF4. And what this will do is provide for a 4-bit format. It's going to compress your model by another factor of 2, so you can fit it into a smaller size of VRAM. I will note though that the speed of the request can be slower, and it can also be difficult to ping the API with more requests in parallel. And I think this is because when you quantize it down even further, there's a lot of dequantization, so expansion back up to 16 bits in the inner part of the GPU that has to happen when the final computation is done in 16 bits. So this is helpful for fitting it into a smaller VRAM, but it may slow down your performance. Okay, there's one more inference I want to show you, and that's the Trellis Mixtral function calling model that's available on Hugging Face. It's a gated repo and you can purchase access. It includes a one-click template. So if I just scroll down here, click on that one-click template, I'll see the function calling model pop up. And again, because it's the same base model as it's the Mixtral base model, you'll want to use an A100 or an A6000 if you want to run it, and you can run it with the same quantization options as I've recommended. So here you would go to A6000, deploy, you can check the setup options. Note, by the way, that I'm setting the volume of the disk to 150 gigabytes. That's to give plenty of space for about 100 gigabytes of the model weights. So I've got that pod running. I had it set up a little bit earlier to save on time. So I'll head over to my pods in Secure Cloud where it's running. And I can check in on the logs just to see that all of the shards have been downloaded, the 19 shards. And furthermore, the shards have been loaded onto the GPU, and my host name here is defaulting to 4 zeros, which means everything should be running nicely. I won't go through the function calls in great detail because that's covered in a very recent video on function calling v3. So let's move on and I'll show you an example of fine-tuning. I'm back over in RunPod, which I typically use for fine-tuning. You can also use VastAI. That's useful in particular for small models and smaller GPUs because they offer lower price points. However, the Mixtral model is quite large. You're going to need at least 2 A6000s or 2 A100s or 2 H100s if you want to be able to fit the model on in full precision. You could alternatively try to fine-tune using QLoRa, and you could probably do that on an A6000, maybe one single unit if you use 4-bit quantization. I think it's probably difficult to fine-tune on smaller GPUs for the moment. So what I'll do is typically I would get started by picking, let's say, 2 of these A6000s and clicking on deploy. Now the template I want to run with is a PyTorch 2.1. It's got pre-installed the NVIDIA drivers as well. It's important to have plenty of disk space when fine-tuning these models. You need about 100 gigabytes for the model once over, but often if you're training different versions and resaving, I like to leave a lot of headroom, so I typically would put that value quite a bit higher. Once that's ready to go, we can set the overrides and then we can move ahead and continue and deploy. Now, while that pod is loading, I'm going to go back to my presentation and show you a little bit of how the training is going to work. So when we have an original transformer for training something like Llama 7B, then often we'll use a technique called LoRa. And LoRa means that we train a small adapter in parallel, and this has got a smaller number of weights. And at the end of the training, we take those trained weights and we merge them on top of our frozen base model weights. And typically we can choose a few different ways to... There are a few ways to select which matrices we want to train. In many of my videos, I might choose to only train the matrices in the attention portion. But sometimes you want to train more parameters and you also will train some of the weights within the feed-forward network. Actually, within the chat fine-tuning video I showed recently, I train using LoRa the weights in the feed-forward and also in the multi-head attention. However, now that we're moving on to the mixture of experts, we're not going to train the feed-forward network. This here is more complex now because there's a router that has to choose between which expert to train, and it becomes more difficult given this advanced architecture to make these parameters trainable and get sensible results. So we're going to focus only on training the multi-head attention. We're only going to train those parameters. And in fact, we're not going to directly train these parameters. We're going to train a small side adapter here, the LoRa adapter, which is typical practice and achieves good results for less memory requirements. So I'm heading back over to my pods and I've got the PyTorch pod here ready to go. I'll connect and connect to Jupyter Lab. Next up, I'm going to upload a file. It's the fine-tuning file. You can purchase the fine-tuning script on its own for function calling. You can also purchase a script for unsupervised or supervised fine-tuning, each on their own, or you can buy access to the full repo. That's the advanced fine-tuning repo. If you do have access to the repo, you get the benefit of all future scripts that I upload to that repo as well. So here I've uploaded a Mixtral script. It's the script I used earlier for training for function calling. Now, a lot of what I'm talking about here is going to be applicable directly to the supervised fine-tuning scripts and the unsupervised fine-tuning scripts and the chat fine-tuning scripts and the long context fine-tuning scripts. The main difference is that we are not going to train the linear layers or the feed-forward layers, but everything else will be very much the same for this training, which I'll demo using function calling. So as per usual, I start off by connecting to Hugging Face so I can push and pull weights, including from private repos. I've set the base model here to Mixtral. Let me increase my screen size a little bit. And I install all the same packages that I typically would install: transformers, bits and bytes if you're using quantization, flash attention in order to improve the training speed. After importing the modules, then I will load the model itself. And here you can see I've commented out the quantization, so I'm loading it in full 16-bit precision using flash attention. Note that this way here of calling flash attention has recently been updated. I give a list of updates now in a newsletter you can find at trellis.substack.com. That's trellis.substack.com. And I'll let you sign up yourself later if you're interested in getting the frequent updates. Back here to the training, and after the model has been loaded, we set up the tokenizer. The pad token we will set to the unknown token. That's a common practice you'll see in many of the other videos as well. The unknown token is already defined in the Mixtral tokenizer. Next up, we will set up LoRa. In fact, first we'll apply gradient checkpointing. This allows us to reduce memory a little bit during trading. And now we're going to print out the model. And you can see here that the Mixtral model has got these attention layers. These are the ones that we are going to train. And it also has 0 to 7, so that's the 8 experts listed here. But we're not going to touch any of this here because, as I said, it's too complicated to try and train this routing network of experts. So we're going to focus on the attention layer that's the same for every expert. We're not going to touch the layer norms either. That's something we do need to train if we're training for longer context length and sometimes for chat fine-tuning, but we're not doing that in this case. We're just looking at function calling. So here you can see when we configure the LoRa, I've actually commented out these layers here that typically I might train, and I'm only training the self-attention layers right here. So once I've set the LoRa config, I get a LoRa model, which basically freezes the base model and creates a set of low rank adapters on the side that we're going to train. Based on these weights, you can see we're only training a very small portion, 0.01% of the parameters are going to be trainable, and it works quite well. So here we'll load a data set. We'll be loading the Trellis function calling v3 data set. You can check that out if you're interested on Hugging Face. It is a gated repo that you can find. I'll put a link down below. It's a specifically designed data set that allows you to achieve function calling performance from a base model. So with this data set loaded and with the data being organized and put into the right prompt format, which is basically the Llama 2 prompt format, nothing too exotic there, we're now ready to examine the data sets and print out our first sample. So I know I'm moving quickly, but you'll want to look back at the function calling v3 video if you want to see more detail. I'm just trying to highlight the parts that are different in the case of mixture of experts. Here, I'm running a test, and the test says you've access to the following functions. I've listed out the metadata for the 2 functions the model can access, and then I ask it to give me the names of the 5 largest stocks by market cap. And you can see that the model does not by default respond with a structured JSON object. It responds more verbosely when we would like it to respond with a structured JSON object. And of course, that's the purpose of the training. So I've run a few more examples here that can later be used for comparison. But let's swiftly move on to the training. And the good news here on the training is that everything is going to be the same. I've used the same learning rate. I've used the same number of epochs, just one epoch for training. And you can see that the validation loss falls down nicely. And once we get to an example after fine tuning, which is just down here below, we'll take a look here, get the names of the 5 largest stocks by market cap. And the model now responds with a structured JSON object and an end of sequence token, which is exactly what we would want. Now you'll notice one little small thing here. It does include a recommendation to search for the biggest stocks in the world. That's just an artifact of how we've defined the functions. It wasn't a required parameter, so it didn't necessarily have to provide that, but it may just have defaulted to that. Okay, once the model has been trained, then the same procedure happens as per usual with defining a new model, which is effectively an address that we're going to push to, and then saving the model and pushing the adapters to the hub, and later merging the model and pushing the model to hub. Now, I did, when I tried to push to hub, have an error with the push to hub for Mixtral, so instead I had to use the upload function from the Hugging Face API to upload the files onto the Hugging Face repo. I'm not sure if that was just a specific issue that I faced. I've created an issue on GitHub, so perhaps this raw mechanism will work for you if you're going to push it to hub, but you can in any case use the upload file or upload folder function if this push to hub doesn't work. Before I round up with this video on Mixtral, just a few highlights on function calling and also on inference. For any fine tunings, whether function calling, supervised fine tuning, unsupervised fine tuning, all the scripts of which are in the advanced fine tuning repo, the key thing to have in mind is that you should not train the feed forward layers. You want to focus on just using LoRa and training LoRa adapters for the attention layers only. Other than that, transformers from Hugging Face works quite well, and it seems that most of the functionality is working smoothly with Mixtral, more or less parallel to how it works for other models like Llama or the basic Mistral model. When it comes to inference, the easiest way to inference right now is using again Hugging Face and the bits and bytes or EETQ forms of quantization, which allow for 4-bit or 8-bit quantization to get that model to fit on one machine. Now there is a GPTQ model from the bloke, and it can be inferenced using the transformers package, but it's not yet supported by text generation inference, which is the API software that I showed you. So if you want to set up an API, I still think it's easier to use EETQ. Over time though, AWQ probably will be supported, as will GPTQ, and at that point I would probably recommend for speed using AWQ for your means of inference. Perhaps you could also use VLLM as well. If you want to check out a video I made recently on inference, you can see more details of using VLLM, and perhaps by the time you see this video, VLLM will be supporting Mixtral, which it's not currently. Alright folks, let me know any questions below, and I'll leave links to all the various repositories in the description. Cheers.